Chemistry Curriculum at Fakir Mohsin University, FMU. The first semester core paper on organic chemistry, CH 416, core paper I, covers stereochemistry and reaction mechanisms in Unit 2. The fundamental concepts are divided into two main components. Part 1, stereochemistry. This section deals with the three-dimensional spatial arrangements of atoms within molecules and how these arrangements govern physical and chemical properties, conformation and reactivity, cycloalkanes and decalins, analysis of chair, boat, and twist boat conformations in cyclohexane and substituted cyclohexanes. Decalins are studied as fused ring systems, cis versus transdecalin. Conformational control on reactivity, how axial versus equatorial orientations affect reaction rates and pathways. EgE2 elimination requires an anti-periplanar arrangement of the leaving group and neighboring hydrogen. Symmetry elements and chirality. Elements of symmetry. Center of inversion I. Plane of symmetry sigma. Axis of rotation C_n, and improper axis of rotation S_n. Criteria for chirality. A molecule is optically active if it lacks an improper axis of rotation, S_n, which includes sigma and I. Projection formulas and isomerism. Interchangeable representations. Fisher, sawhorse, Newman, and flying wedge projections. Thrio and erythro isomers. Terminology used to describe diastereomers having two adjacent chiral centers with similar functional groups. Optical activity and configurations. Absolute. RSS nomenclature using CIP rules, and relative configurations, prochirality and topicity, enantiotropic and diastereotropic atoms/groups/faces, distinguishing homotopic, enantiotopic, and diastereotopic hydrogens or carbonyl faces using substitution and addition criteria. Asymmetric and selective synthesis, stereospecific versus stereoselective reactions. A reaction is stereospecific if the mechanism dictates that a specific stereoisomeric reactant yields a specific stereoisomeric product. Stereoselective reactions predominantly yield one stereoisomer when multiple are possible. E/Z notation. System for defining geometrical isomerism in alkenes based on CIP priority rules. Part 2. Reaction mechanism and quantitative structure-reactivity relationships. This section focuses on the energetic profiles, intermediate pathways, and quantitative metrics used to determine how organic reactions occur. Thermodynamic versus kinetic control. Thermodynamic control produces the most stable product, lowest free energy, delta G circ, favored at higher temperatures and longer reaction times. Kinetic control produces the product form fastest, lowest activation energy, delta G dagger, favored at lower temperatures and shorter reaction times. Hammond's postulate and energy diagrams. Hammond postulate states that the transition state of a step resembles the structure of the species, reactant, intermediate, or product to which it is closest in free energy. Potential energy diagrams, tracking energy changes across multi-step reaction profiles. Isotope effects. Primary kinetic isotope effect, KIE. Meant to determine if a specific CH versus CD bond is broken during the rate-determining step. K_H divided by K_D, approx 2 text 7. Secondary Chi-E evaluates hybridization changes, e.g. sp3 to sp², at non-cleaved bonds during the transition state. Linear free energy relationships, LFER. Hammett equation relates reaction rates, K, or equilibrium constants, K, of meta and para-substituted benzene derivatives to substituent constants, sigma, and reaction sensitivity constants, RRHO. Taft equation extends the Hammett treatment to aliphatic systems by separating electronic inductive effects, sigma_*, from steric hindrance effects, E_S.